Hello everyone, I'm Seunghyup Yoo at School of Electrical Engineering in KAIST. It is my great pleasure to share our efforts on harnessing organic optoelectronics for wearable healthcare. Since I joined KAIST in 2006, my research group called Integrated Organic Electronics Lab, or IOEL, has been exploring the possibility of using organic electronics for display, energy, and flexible electronics applications. Major research efforts include device and process innovation in organic light-emitting diodes, or organic solar cell and perovskite solar cell, as well as organic TFT and integrated circuits. Key advantages of organic devices include optical richness and its thin film nature and low temperature processing, which results in unique form factors such as transparent devices and or flexible, rollable, foldable, and even stretchable devices. For this reason, OLEDs are now a popular choice for high-end displays and those exploring their versatility in form factors. OLED displays in foldable smartphones and rollable TVs are good examples. But these high-end displays are not the only application of organic devices. There can be ample opportunities in wearables where form factors do matter. In particular, wearable healthcare applications are expected to be highly beneficial to the society and have a strong market potential. So in this respect, I'm leading a multi-university interdisciplinary research center located at KAIST, trying to make OLEDs and other modern light sources useful for wearable phototherapeutic applications. One of the key achievements in this center include the work done by Professor Kyung-Chul Choi at KAIST and Professor Kyung-Chan Park at SNU Bundang Hospital, which demonstrate that a patch-type wearable OLED producing red to near IR can promote the healing of the damaged skin for point-of-care wound treatment, which illustrate the immense potential of OLEDs when its wearable form factors are combined with medical applications. In such body-attachable applications, ultra-flexible or stretchable form factors can be especially important. This is an example of the work we worked on for realization of ultra-flexible OLEDs. Based on 6-micron thick ultra-thin substrates and a careful design considering neutral plane shift in systems on such ultra-thin substrates, these OLED exhibit high performance and near-foldable flexibility, even with conventional transparent conductors and alumina-based encapsulation, which are known to be prone to bending-induced fractures. Furthermore, we have recently demonstrated stretchable OLEDs so that OLED patches can accommodate body movement. So being combined with serpentine-shaped interconnecting electrodes, the stress-relieving layer based on low Young's modulus material called Sylvion led to highly stretchable OLEDs, the interconnecting electrodes of which can be stretched up to 140% with a performance comparable to conventional rigid devices. Now let me introduce to you OLEDs and OPDs, organic photodiodes, can in fact do a very good job in heart rate and blood oxygen level measurement for wearable health monitoring sensors. Heart rate can be measured with so-called photoplasmogram, often called PPG. So it measures the volume change of blood vessel associated with cardiac cycle by monitoring the degree of change of absorption through the blood vessel. It can be measured either in transmissive or reflective types. Blood oxygen saturation monitors concentration of oxygenated hemoglobin with respect to the total concentration of hemoglobins. The human body requires and regulates a very precise and specific balance of oxygen in the blood. in which breathing and delivery by oxygenated hemoglobin play a major role. And oxygen saturation level in blood, also called SpO2, serves as an important vital signal. SpO2 can be measured by comparing PPG signals measured at two different wavelengths, let's say lambda 1 and lambda 2, where absorption coefficients are same and different respectively for hemoglobin with oxygen and without oxygen. A combination of green and red, or IR and red, can be used for light sources with such two different colors. We are not the first one who worked on organic PPG and SpO2 sensor. Professor Arias' group at UC Berkeley demonstrated that organic LED and organic photodiodes can be used for such purposes. And after that, Someya group at University of Tokyo and our group, together with Professor Haejun Yu's group in KAIST, demonstrate that organic SpO2 sensor can be useful for patch-type wearable sensors. While these previous works mainly focused on the form factor advantage provided by organic technology, this is not everything. For any sensor technology to be practical, one must make reasonably power-efficient devices. Even with a duty cycle and interval operations, light source in ultra-compact or thin-film wearable devices may not afford power consumption larger than milliwatt, considering that battery compatible with such form factors typically have very limited capacity. Can we then make organic SpO2 sensor have such a low power consumption? To answer this question, we first look at the geometry of our sensor, which is similar to the side-by-side arrangement found in conventional SpO2 sensors. If you look at this photo on the right side, you can easily tell that the light propagating in direction indicated by these arrows will be mostly wasted and does not contribute to the meaningful signal. To better understand and design an efficient SpO2 sensor, we have carried out an optical simulation for light propagation inside the human skin. It does indicate that light propagates in all directions through a scattering from many organelles like mitochondria and lysosome, and they have sphere-like shape and on the order of micrometer scale, and thus can be simulated approximately as a Mie scatterer. One more thing to note is the lateral propagation length. You can see that red light spreads wider than green light, and this is due to the fact that the human skin has lower absorption in long wavelength range than in short wavelength range. Considering the fact that the photodiode noise continues to grow with the square root of diameter, detector area, and that the signal gets saturated at some point due to the finite lateral propagation length of the light, we were able to identify the optimal dimension of concentric geometry where organic photodiodes wraps around circular OLED. We then utilized easy patterning capability of organic technology to realize an ideal design that can make a smarter use of photons than conventional linear arrangement of LED and photodiode. So in the proposed scheme, a photodiode looking like alphanumeric character 8 wraps around the green and red OLEDs as shown here. So please note that the circle around the green light is smaller in diameter than that surrounding red OLED. This is the actual photograph of sample we fabricated with the device structure shown below. We used the state-of-the-art phosphorescent OLED for red and green light sources and C70 TAPC bulk heterojunction organic photodiodes, which have a decent responsivity in the visible spectral region. This is another photograph of the actual sample we fabricated. The overall devices were encapsulated with PET with embedded barrier films under phase seal geometry. And interconnecting electrodes for connections were done for ACF or anisotropic conductive films. You can see here in the right side actual operation of our pulse oximeters. So custom designed circuit board was used in collaboration with Professor Hoi-Jun Yoo's group in our institute. With the proposed approach, we were able to demonstrate reflective SpO2 sensor that can operate it at 17 microwatt for red and 31 microwatt for green. This is a significant reduction in power consumption with respect to conventional reflective pulse oximetry sensor, which require about milliwatt to several hundred microwatts for operation. Ultra-thin flexible OLEDs are realized even with conventional transparent conductors and alumina-based encapsulation by carefully monitoring the shift in neutral plane in devices on ultra-thin substrates. Stretchable OLEDs were realized using a rigid island platform by incorporating a low Young's modulus stress relief layer. OLED OPD combination was shown to be promising not only for flexible wearable form factors, but also for sub-100 microwatt SpO2 sensor for all-day wearable monitoring with a smart optical design. Finally, I'd like to thank the funding agency and Dr. Kondo and Mr. Song who helped this work, and you for your kind attention. Thank you.